All right, everybody, recording has started. On Thursday of last week, at the beginning part, or not Thursday, you guys had Wednesday of last week, the first part of the block, we talked about developing what we refer to now as the quantum mechanical model of the atom. What's the gist of the quantum mechanical model of the atom? Or what does our current model of the atom look like? What's one of the key features of it? Make it good.
It's got rings, alright.
Does it have rings? Good. It's got the energy levels, but what did we say within those energy levels, though? Especially about electrons. Good.
The location of electrons cannot be
Good. That the exact location of those electrons can never really be known. That we can give an area of high probability of finding electrons, but we'll never actually know where electrons are. And that leads us to this picture of the atom, or this model of the atom, which we refer to as sometimes the quantum mechanical model, or sometimes we'll refer to this as the Schrodinger model. Okay? Notice, nucleus is going to show up right in the middle, right? That blue dot representing the nucleus. It is small compared to the rest of the volume of the atom. That part still applies. But then we have these dark bands that exist within this, not within that house, sorry. Those dark bands exist like in this area here, then a little bit farther out, then a little bit farther out, right? Dark band here, dark band here, dark band here, with some space in between those dark bands. Is it completely empty space between those dark bands? No. All right. Each of those dots, we said, represented, try on one of, that shelf right there, or where the,
yeah.
Is it good? Yeah. Each of those dots do not represent an electron. That's way too many electrons to be in one atom. They represent places where electrons were at a specific moment in time. Right? And that's where we start seeing these darker areas, because electrons spend more time within certain areas around the nucleus as opposed to other areas. Also keep in mind, this picture is representative of a three-dimensional shape. These circles aren't really circles. They're more like spheres, but I can't draw them like spheres because I only have a two-dimensional board. So keep that in mind as we move forward here. Okay? Are we good with that? I believe on Thursday or Wednesday, we got this, right? Summarizing what we just talked about. Based on the work of Heisenberg and his uncertainty principle, Schrodinger and his wave equations, we get to the conclusion that the exact location of electron will never be known. But the wave equations that Schrodinger develops give us an area of high probability or high electron density. And that gives us, even though we don't know for sure where those electrons are, we can have a pretty good guess. Okay? Good so far. We try to distinguish those areas where we find electrons, or where we are most likely to find electrons, by using these quantum numbers. Each of these areas where there is high electron density, which equates to a high probability of finding electrons, it has a set of 4 quantum numbers that distinguishes it from other places. And that's where we got into a little bit on Wednesday. We'll get into that way more on Thursday, or today. Remember, these are not the exact location of electrons, but the most probable location. And we're trying to distinguish those probable locations from other probable locations with this set of 4 numbers. Okay? Good there? All right. The first one that we talked about was the principal quantum number. We use the lowercase letter n to represent the principal quantum number. If we talk about it in the analogy of this being an address for the electron, right? This would represent the electron city. A big area where a lot of electrons may exist. Okay? If we go back to our picture of the atom, our Schrodinger model or our quantum mechanical model. The principal quantum number represents these big dark areas. So there's this part right here. This is a, oh, not what I wanted to do. Come on, give me the yellow, there we go. Each of these yellow areas that I've highlighted represent a principal energy level. And therefore, each of those areas is assigned a different principal quantum number. Okay? Good so far? We use the lowercase letter n to represent that principal quantum number. So this would be n equals 1 here, this would be n equals 2 here, and then this will be n equals 3 right there. Is that good so far? We said that principal energy levels also tell us something about the properties of those electrons. What do the principal energy levels tell us about electrons or electrons within those principal energy levels? Minga, go ahead.
How much energy you have?
How much energy they have? Minga, give me a little bit more detail than that.
The electron is on the outermost level as the most energy,
Good.
and if it, as it goes in, then it loses energy.
Electrons that are at energy levels closer to the nucleus have less energy. Electrons that are in energy levels higher, farther away from the nucleus, have more energy. So if we're talking about these numbers, principal energy level n equals 1 has the lowest energy electrons. Principal energy level n equals 2 have more energy, n equals 3 have more energy, etc., etc., etc. Okay? Good there so far? All right. Let's take a look at principal energy level 1, n equals 1. There's this big dark area right in the middle. Okay? Why is that area so densely populated with electrons? Or why does that area show up so dark on our picture? Nate?
Because when electrons get energy, they don't want to keep it, so they go towards the center.
So it is a lower energy level. That's why it's that's why it's densely populated. Okay? What's another reason why that area might be densely populated? I think you already answered a couple questions. Nate, go ahead.
Because there's protons in the nucleus.
Right in the middle of that densely populated area, there is a nucleus that has a positive charge. And electrons have what charge? Negative. So are they attracted to that area? Yes, they are. What we find out, though, is that even though this is a very, very dark area on the model, there aren't that many electrons in that space. It's very dark, but that doesn't mean there's a lot of electrons. That just means there's electrons there a lot of the time. Why might there not be a lot of electrons in that space? Okay, good.
Because each element can have a certain number of electrons.
Why?
It distinguishes the element.
Yeah, although as we get more and more elements, they get more and more electrons. How come they don't all just end up in that space right there? Emma?
Because electrons are all negative and negative, they don't want to be next to each other.
Good. Even though the electrons that are there don't leave here very often because it's a low energy space and because they're attracted to the nucleus, not a lot of electrons exist in that space because they all repel each other. That's where we start getting these certain areas around the nucleus where we're more likely to find electrons. It has to do with how hard is the nucleus pulling them in versus how much are they repelling each other. Okay? Good there so far? Okay. What we're going to do now is we're going to zoom in on this level right through here. Actually, I should have done that in blue. Okay? You'll see why in a second. Okay? We're going to basically zoom in on that area. And what we find if we zoom in on that area is that within that dark band, there are certain areas that are more densely populated with electrons than other areas. Like, for instance, in Westlake. Are there areas of Westlake where more people live, and there are areas in Westlake where less people live? Yeah, right? If you go into a neighborhood, right, like Settlers Reserve, you'll see a lot of people live in that area there. But if you go to, like, Bradley Reservation, are a lot of people living there? No. So there's areas, even within Westlake being a very populated city, there are areas within that city that maybe aren't so densely populated. And that's what we're going to get into now. Okay? All right. The next quantum number that shows up is the angular momentum quantum number. First, I'm going to give you the rundowns of the angular momentum quantum number, and then I'll tell you how it applies to what we're doing. Okay? So first, we use the lowercase letter L to represent the angular momentum quantum number. A lot of times you'll see it written kind of like a cursive L to sort of, distinguish it from a letter 1 or, okay, so you guys see kind of like a cursive L, something like this. Right? Okay. And that represents like the electron street. Within the city of Westlake, there are streets that are more densely populated versus other streets that aren't as densely populated. Within each principal energy level, areas with greater electronic density exist, and we refer to those levels or those areas as sublevels. Just like we said, within Westlake, there are certain places where more people live. We call them developments. Okay? Within the principal energy level, there are greater electron density in certain places, and we call those areas sublevels. What we find out is that these sublevels start showing a distinctive shape. And we give these shapes different letters to distinguish them from one another. And on your outline, you'll see that we have those shapes at the top, or kind of towards the top of page 2. Okay? S orbitals. S orbitals have a spherical shape, and we refer to them, we give them the angular momentum quantum number of L equals 0. There we go. Okay. S orbitals have spherical shape. We give them an L equals 0 quantum number. P orbitals kind of look like figure 8s. Right? They have these two lobes on either side of them. P orbitals we distinguish by giving them the principal quantum number, L equals 1. D orbitals, you might have to draw the D orbitals in a little bit because they didn't copy very well because it's a yellow picture and yellow doesn't copy very well, but you can kind of see there, okay? D orbitals kind of have this X shape, and we give them the angular momentum quantum number of L equals 2. We start seeing that patterns start showing up into how these electrons settle around the nucleus. And then the last type of sublevel is the F sublevel, which we represent with L equals 3, but they're pretty complex as far as the shapes are concerned. So we're not going to get into that too much as far as what they look like. Okay, good with that so far? Let's see how this all starts fitting together in our model of the atom. So let's get out of here. Oh. And let's go here. This red dot, or this red area, represents a sublevel, an area where electrons are likely to exist. Okay? It's very close to the nucleus. It's filling in this first big dark area that's close to the nucleus. So what principal energy level is it? What N value does it get? That's the big one. Okay? It's the first dark ring around the nucleus, so it gets the N equals 1 value. But, Joe, what shape is it? It's a circle. So that means its L value is 0. This is an S orbital. How do I know? It's a spherical shape. We refer to that shape as an S orbital. Good so far. Now, I mentioned before, but just keep in mind, this is a two-dimensional representation of a three-dimensional thing. think of it kind of like what I'm about to show you. Think of this kind of like those little like Russian dolls that there's like a little one and then like the one goes over it and then one goes over that and then one goes over that. Does that make sense? Okay? That's what I'm about to show you. Okay? Notice right after that big dark shape, there's this lighter area. And then we get another dark band that shows up right through here. Okay? That's where we're going next. It looks like this. Does everyone get that representation? The red is inside of the blue. Okay? This is the next area that we find a lot of electrons, that we find a high electron density. But because it had that lighter area in between, we've now jumped up a principal energy level. This would kind of be like on Bohr's model, right? We went from one ring to the next ring. But keep in mind that it can't just exist on the rings, but it's kind of like that. Does that make sense? Okay. So now, because this is a new energy level, it gets a new principal quantum number. We're now in the second energy level. But Joe, what shape is this still? It's still a circle, so that means what value do we get for its L value? It still gets a 0, even though it's in the second energy level. These two, this red sphere and this blue sphere, have a different set of numbers, right? It's like somebody who lives in the same street as you, but now lives in Rocky River instead of living in Westlake. Does that make sense? Right? It's like a cul-de-sac in Rocky River versus a cul-de-sac in Westlake. Good there? What we start finding out though, remember I said, this next part here, we start zooming in on this big dark area that exists around the nucleus, this area right in here. Okay? Ooh. Undo. What we start finding out is that these little bumps start showing up kind of on the outside. Kind of like, I don't know, Mickey Mouse ears or something like that, if you want to think of it that way. These are areas of higher electron density. They exist just outside of that sphere, but they're still connected to it. And that what we find out here is that we get another little set of bumps like this, and then another set of bumps that kind of look like this, but one comes out of the board and one goes into the board. Does that make sense? Okay. X-axis, Y-axis, Z-axis. Okay. These are what we refer to as the sub-levels. If we look at them in isolation, right, here, even though they're not connected, what shape is that sort of forming there? If you look at your picture that's on page 2, right, what does this most closely represent? This is not L equals 2. This is more of a figure 8 shape, yes, even though it's not connected because there's other stuff in the middle of it. Does that make sense? This is a figure 8 shape. Okay. So here, this part, right, these bumps that start showing up on the outside, they're still in the second energy level. So that's still n equals 2. But now they're a different area. So we distinguish that like this. Does that make sense? This is a p orbital. It's an area outside the sphere where we're starting to find more electrons. Okay? Greater probability of finding electrons just outside of that sphere in these areas. But what we find out, that isn't the only place that we find these electrons just outside the sphere. We'll also find them here, kind of up and down-ish, and then we'll also find them here, sort of into the board and out of the board. Is that good there? Okay. These are the sub-levels. Notice, they're all blue. They're all within the same principal energy level, but they're areas of greater density. Okay? This is like Settlers Reserve. It's an area within Westlake where a lot of people live. This is like Musical Streets. It's another area in Westlake where a lot of people live. Does that make sense? What it's looking at? They're all Westlake, but there's certain areas within Westlake where people live. Greater electron density. Good there? Okay. All right, let's go back to the outline for a second. find out is that these energy levels start showing up in a pattern. All principal energy levels have an s orbital. So every time we jump from one quote quote ring to the next quote quote ring, it starts with a sphere. And you'll see that in just a second. The next one are these p sublevels. That's the figure 8 type shapes. They start showing up next, but they don't start showing up until we get to the second principal energy level. Were there red p orbitals? Sorry, right. Third sublevel we labeled D. D's don't start showing up until the third principal energy level. And then the fourth sublevel is called F. F's don't start showing up until the fourth principal energy level, and to be quite honest with you, we're not going to get there because it's really complex and hard to distinguish. But we differentiate those different levels by using the different L values. All right, good so far. All right, good so far? Okay, let's go back to the picture. Okay. We already said that this sublevel right here, it's in the second energy level. It's blue, therefore it has an n equals 2 value. Joe, what shape is it? It's a, no, this one. It's the figure 8 shape, right? So that gives us L equals 1. Okay? However, if we take a look at this one here, right? It's in the second energy level, so it gets an n equals 2. But what shape is it? Figure 8. That means it's what kind of a sublevel? We just call it a what sublevel? L equals 1, but that represents the P sublevel. So that means L equals 1. What are we starting to see here about this set of quantum numbers? From these two numbers, can I distinguish this one from this one? Same so far. That's where the third quantum number comes in. We call this quantum number the magnetic quantum number. First, we use the lowercase letter m with the L subscript, or you could just use lowercase m, which is what I'll probably do. Okay? So let's just say, lowercase letter m. Okay? This represents the electron's house. Anybody in here live on the same street as somebody else? I guess friends like live down the house. I mean, I know you all live on the same street as other people, but anybody like in this class, you guys like neighbors, known each other since the 2nd grade or something like that. Anyway, so you guys live on the same street? Okay, so, well, do you guys, like, is your address like different numbers but on the same street? That's what I want. But anyway, you guys get the picture, okay? Your next door neighbor. Your next door neighbor lives on Main Street in Westlake, Ohio, even though there is no Main Street in Westlake, Ohio. But they're clearly different places there. Those two pictures, right, those two p orbitals that we were just looking at, they're in the same energy level, they're both blue, and they're both p orbitals, right? But they're clearly different from one another. Okay? Within the sublevels, there are these things that we call orbitals. Orbitals are three-dimensional areas of high probability of finding electrons. Every single thing that I've drawn up on the board today has been an orbital. It's an area where we find a high probability that electrons will be there. Each orbital can only contain a maximum of 2 electrons. Why? Why won't we find more than 2 electrons within the same space? Going back to something we talked about at the beginning of class.
Because they repel each
They repel each other. There's only certain areas where they're settled in. And those areas can't be too crowded, because if they are, they'll just push each other away. Okay. Got that so far? What the magnetic quantum number does for us, it indicates which of those orbitals that the electron is in. For example, we find that there are 3 p orbitals. So you have to distinguish one from the other from the other. We kind of already started implying that for p orbitals, those electrons will exist one on the x-axis, one on the y-axis, and one on the z-axis. So which orbital are we talking about? Where is this electron exactly? It's in the second energy level. It's in a p orbital, but there's possibilities there. It indicates the orientation of that orbital around the nucleus. What we find out is that within the p orbitals, they all look the same, but they're all different orientation around the nucleus. And that's what that picture down at the bottom is showing you. How do we distinguish them? We say that the possible values for the magnetic quantum number run from negative L to positive L. Joe, you've been working on this. For the p orbital, what value do we give for L? 1. For these values, negative L to positive L, that means it can run from negative 1 to 0 to positive 1. So how many p orbitals can there be? 3. Look at your picture on page 2 of your outline. How many pictures of p orbitals do you see in that chart right there? 3. For d orbitals, what value did we say that we gave for L on a d orbital? 2. If we go from negative L to L, negative 2, negative 1, 0, positive 1, positive 2. That leaves us with how many possibilities? 5. How many d orbitals are pictured there in your chart? 5. Coincidence? No. So let's go back to this picture. We've already established that we're sort of running into a problem here with this p orbital and this p orbital. Because they're both in the second energy level, they're both p orbitals, so the first 2 numbers are the same. That's where the m number comes in. What axis is this one on? X-axis. If you look on your notes, we gave the x-axis a certain m value, right? What is it? Negative 1. This one's on which axis? Y-axis. So that means that its m value is equal to 0. Okay? This one, right in the middle, it's on the z-axis. Oh, too far. It's on the z-axis, but it's still in the second energy level. It's still a p orbital, but it's different from the other ones, yes? So we give it a different m value. We call this one positive 1. Is that good so far? Okay. You just wrote down, when we were talking about magnetic quantum number, how many electrons can exist within each one of these orbitals? How many electrons can exist within this p orbital right here? 2. Most likely, one's going to be over here and one's going to be over here. Why? They repel each other. They want to try and get as far away as possible. So we got to have a way to distinguish this one from this one. And that's where we get to the spin quantum number. Spin quantum number, symbolized by the lowercase m with the subscript s, or a lot of times we'll just use s. This is the electron's quote-unquote room in the house. Even if you have a brother and sister, you guys have the same address. But does that mean that you guys hang out at the same place all the time? Not necessarily, right? There's probably some space in your house that is designated as yours. Maybe. Hopefully. Okay. But each orbital can only hold 2 electrons. We call that the Pauli exclusion principle, which we'll talk more about tomorrow when we talk about electron diagrams. Sorry, orbital diagrams and electric configurations. These electrons have different quote-unquote spin to distinguish them from one another. That means that there can only be 2 possible values for spin quantum number. We either call it +1/2 or -1/2. Does it really mean the electrons spin in opposite directions? No. All it's saying is we have to distinguish one part of this orbital from another part of this orbital. Does that make sense? So if we go back to our picture, hold on a second, we still got 3 minutes left. Here, this one we've already established is n equals 2, l equals 1, m equals -1. If we go this part right here, this is still n equals 2. This is still L equals 1 because it's still a p orbital. It's on the x-axis, so that means its m value is -1. But, not that, but here and here are 2 different places. So that's where the spin number comes in. So we call this side +1/2 and this side -1/2. Because with 4 different numbers, you can distinguish all of them differently. For example, hold on, we're not done yet. Easy. Let's go here. Okay? I added another stacking doll onto this thing, right? Remember we said it was like a little doll and one stacks on the other, one stacks on the other, okay? Here's the next energy level. So if we take a look at this one right here, it's in the 3rd energy level, so n equals 3. Okay, this is on your test, that's all I'm saying. It's a p orbital, so L equals 1. Which axis is it on? It's on the x-axis, so its m value is equal to -1. I know I should have used something different besides yellow, but I picked yellow. So. But then, that would also be true of this one over here. N equals 3, L equals 1, m equals -1, but now we got to distinguish it from the other part. So that's where the s value comes in. +1/2, -1/2. With 4 numbers, we can distinguish all of these different parts from one another. Okay? Maggie, good.
How do you decide which one's positive 1/2?
It doesn't matter. Okay? Really, that's up to you. Is it really that the one on the left is +1/2 and the other one is -1/2? No. They just have to be different from one another. Okay? And Maggie, that leads you to another question. Does the x-axis always have to be -1 and y-axis 0 and z-axis +1? No, not really, because if I twisted this 90 degrees, they'd all be different anyway. As long as you distinguish them one from the other, that's fine. Okay? Yeah, go ahead.
Okay, I'm a little bit confusing about D, so I'm so unsure.
Don't worry about D right now. Okay, let's just stick with S and P, and that'll help us for a while. Okay? All right, hey, oh, wait, hold on, freeze. On the calendar, the homework section. It says there are 2 links. One says problems, one says answers. Your homework tonight is online. It is a PDF. Print it out. Work on it. If you're having trouble, don't worry about it. We'll come back and deal with it tomorrow.
I'm gonna drop this off inside. My side, you have a Sharpie.
No.
Numbers and
No.